So in this particular video, we go over matrix algebra. In the previous one, we went over how to define scalar multiplication of a matrix. I defined how to take the addition of two matrices. And we also discussed how to take the product of two matrices. And those operations were, in many cases, a lot like vectors, except for matrix multiplication. So in this video, we talk about not the actual act of doing the multiplication, but ways to manipulate symbols of products of sums of these matrices so that we can think of it on a higher level when we manipulate these particular objects. So what we need to do then is I'd like to go and extend the ideas of linear combinations from vectors to linear combinations of matrices. There's a couple reasons to do so. The main one is because it's so easy to do so. And the second one is because this idea of linear combinations is going to go throughout the entire course. We're never, ever going to get away from it. In fact, almost everything we do, all our basic assumptions are set up just so that we can form linear combinations. Immediately after that, I'll talk about the basic algebraic properties of matrix addition and multiplication. And I'll show you special ways to take products of certain matrices to do them quickly so that you don't have to do it the long way every time. So the first one is just the basic algebraic properties of matrices. Now, all these properties pretty much come straight over because of vectors. You can think of a matrix as just being a vector that instead of being long, it's been kind of wrapped into like a square. So because of that, all the properties you learned before should still be true. So let's say you have matrices A, B, and C that are all the same size. That way their addition is defined. And let C and D be any scale as you like. Then all 8 of these properties, these are the properties that we need in order to define linear combinations. So the first one's called commutativity. The second one's called associativity. Associativity is important because since the parentheses are not needed, either way you get the same sum, we can then write down summations without parentheses. 3 and 4 are important for simplification purposes. They show you how a matrix is related to its inverse minus A, and how a matrix plus the 0 matrix is just a matrix. 5 and 6 are called the distribution properties. It shows you how to distribute a scalar through matrix sums, or how to distribute a scalar sum into a matrix. In each case, it just distributes through. The last one, not the last one, but 7 is associativity of constants, which means that if you have a constant times another constant, and those constants are just willy-nilly throughout the expression, you can just combine them. Just put them out front of the matrix. It's just easier that way. And then lastly, 1 times A is just A. These are the main 8 properties that we need in order to define linear combinations and to do the algebra that we would like to do. So just as an example, let's suppose that you have this particular matrix here. And I want to know then, what would this X be? So one of the properties is distribution. I can just multiply the 2 through. Another one of the properties is I can reassociate scalar multiplication. So this should be 2 times 3 times X. But instead, I'll just do 6X, and that would then equal to 3A. I can then subtract 2A on both sides. Think about all the things you have to do, though. To subtract 2A on both sides, I'd have to first do it on both sides. I'd have to collect the minus 2A and the plus 2A to get a 0 matrix. I'd have that 0 matrix minus 6X, that'd be the minus 6X. That's why you need all those properties. And on the right-hand side, I would then have 3A minus 2A. And by the distribution property, that's the same as 3 minus 2, which is 1, A. And 1 times A is A. Again, I just used those 8 properties. I just said them to you as I went through it. And then from here, you could then multiply both sides by -1/6, which requires to do the association trick. You associate the -1/6 and the -6 together first to get 1, and 1 times X is X. And on the other side, of course, you'd have -1/6A. And that's the answer. So those 8 properties are the things you need in order to do that kind of algebra. Okay, so then I think what we should do then is that you should see at least why these things are true. Now, I've back before with vectors, I showed you how to prove one of them. I'll do another one here. It's very similar to how you would do how would you go about proving the same exact properties, but with vectors. So let's prove that if A and B are matrices of the exact same size, then A plus B will equal B plus A. Now, why am I doing this? The reason is that very soon we're going to get into computations where if you do not know how things are expressed, you'll just start taking it as magic. And you won't be able to go and express things on your own or figure things out on your own. You'll be stuck on the numerical level forever, which is really unfortunate because you won't be able to do very much with linear algebra. You'll be able to, if someone says, do this problem, you probably can do it, but you'll have no idea how to take a similar looking problem and apply the same techniques on it because you never got to the lower algebraic or geometric levels. So how do we do this? When you look at that equation, it's really saying two matrices are equal. So then if you remember the definition, two matrices are equal if and only if they have the same size and corresponding entries are equal. So first off, notice that the two matrices have to be the same size because if A and B are the same size, then of course their addition in either order gives you the same size matrix. Now what I'll do is I'll show that corresponding entries are equal. The common way to do that is to work on one side and look at the ith jth entry. Just don't tell me what I and j are. We'll look at the ith jth entry, and then I'll prove to you that it's the ith jth entry of the other matrix. That means corresponding entries would have to be equal. So here is the ith jth entry of the matrix A plus B. Just by definition, the ith jth entry of A plus B is find the ith jth entry of A, find the ith jth entry of B, and just add them. Now, those two things are numbers. A sub ij and B sub ij, they're just numbers. So because now they're just numbers, we know they commute because that's one of the properties of normal everyday addition. But that expression is actually the ith jth entry of the matrix B plus A. Again, that's by definition. So that means then the ith jth entry of A plus B equals then the ith jth entry of B plus A. So then corresponding entries of these two matrices are in fact equal. And I think that's enough for this video.